So in the past, we looked at time series basics. We went through ETS decomposition and forecasting. How do you decompose into trends, seasonality, and error, and what's the difference between seasonality and cycles. Also looked at the various exponential smoothing, like as a theoretical basis, and Arima, Sarima, Sarimax, and then Facebook Profit. Just a brief introduction, and then so today we are going to take one example, airline passenger, and code through all of these functions. So we will touch pretty much every one of these, and going through different methods. So there are many places where there is improvement that can be done. For example, you can do feature engineering or do parameter estimations efficiently and so on. But the objective today is not to go through that, but generally go through various methods and get familiarized with a very simple data set. So let me show you the data set that we are going to work with. So it's a airlines passengers data. This is a month collected from 1949, and then it says how many people were traveling during that month, and it's 112,000, right? So if you go all the bottom, it's until 1960 December 432. So we are taking very simple data set, and we're going to try to forecast into future. Maybe we'll break down at certain point and forecast into future. Um, so before I get there, so this is the outline of today's this video. So you have we will just set up few things and then read the data and then do decomposition of the data and show you how the code looks like and what the output will be. Then we will look into some smoothing functions, simple smoothing function, Holds method and Holds winter method, and then Arima and Sarima, and how to do auto Arima and use these parameters into Arima, and then we'll do Sarima, and then example of Sarimax. Essentially it's a Sarima, but we are going to add exogenous variable and make it and then we have this profit, which is a model, statistical model coded in Stan. It's similar to one of these methods, but they automated a lot of stuff. So we will also go through some of this code. And neural profit is a very recent extension of this one, or uh, and then we'll also try to see how to use LSTM model to 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 do forecasting, and then XGBoost, which is a machine learning approach. I think these you can think of these two as machine learning approach, and then the profit, Arima, Sarima, and smoothing functions as a statistical approach. So the goal here is to go through this example and go through various methods, and as you dig deep into it, you will learn how to refine them. So we are not trying to become an expert, but just get familiarized with a simple data set to do forecasting. Okay, so that is our objective, right? So this is one way I set up my path. So I have a notebooks directory and a data directory and images directory and the project that I'm working on. And then if there are any utility functions, I can write into it that this one DS utils or plot utils, and I can import them. And this code helps us to put that in the path so that we are not confused about looking for where these folders are. So I wrote two functions, and you will see in later code why this is going to be useful. So uh, get airline data. So essentially I'm reading this airline passenger .csv, which is this file. You can see these are a string, and these are coded as a year and month, and then number of passengers in thousands. So that's the data we read in, and then we are trying to we convert month into a date format, right? So into date format, and then we are adding as an index. So since there will be extra month column, we are removing it and then creating the other column as num passenger. So this is our airline data set. You can see what the output is going to look like as a data set. So I also created a get, train, and test data set. It's a simple data set. So I created So train DF as starting from 1950s, it's starting from 1949. So you can see here from 1949 to 1956 December. So it will go 1956 December, yeah, until almost like 97 rows. So that's how many in lock, unlike range, it includes this particular data as date as well. So that's some confusion we might get into if you are not used to using lock .loc. But and then this one will be from 1957 to the rest of the data. So that's a train data set and test data set. So you can see here the head and tail, and if you plot it, you can see there is an increase in number of people traveling from 1949 to 1960 December. So we will write couple of plotting functions, and I will just demonstrate you what these are. So these are some metrics that we are going to use. These are for any time series. We are generating series of numbers. So that series of numbers are going to compared against another series of numbers. So you can do validation using, it's a continuous variable, so you can see mean square error or root mean square error, so that the scale is similar to the variables that we are using. And mean absolute error, you're differentiating the difference between the actual value, true value, and predicted value, but absolute value, and you're taking the mean of its and then MAP is mean absolute percentage error. So these are four metrics that we are going to print out. And then to do the plotting, plot and validate. So when I say plot, I'm trying to, because this is a series of data, we can plot cleanly in this way. So for example, here I took a train, and then the variable is number of passengers. You can see I'm calling here, and then I'm plotting label is equal to train and legend is equal to line width is equal to 2. So the same thing I'm doing test and also prediction. So if I have a prediction variable that way, and then when I do validation, I just call this function and it will print all of these. Right? So these are going to be useful going forward. So I did get a train test data and passed for prediction test DF for now. So you can see the plot as this way. Okay. Now we will start with our first statistical function, which is to decompose the data into a trend and seasonality. So this is the original data, and you can see the trend is increasing. So sometimes you may want to know whether this is a linear increment or exponential increment, or if it's a linear, then you use the additive trend, and if it's a exponential increment, you use a multiplicative trend. Seasonal, you can see I think around summer or so, I think the value is increasing. So there's a seasonal component after taking out the trend. This is what you see, and this is whatever we cannot explain with these two, right? So, and if you want to plot only one of those, you can just get the result, and you can get trend and plot in this figure. So smoothing functions. So these are if you look at this data, I think it is in a way, when you look at you're trying to come up with a function that is that averages out in a way. If it looks somewhat zigzag, so the smoothing function tries to come up with a average estimate of the points here. So there are many ways of computing it, and we are going to do one way is to do the pandas way, which you take the continuous variable and you're using this so we can do this EWM and then provide. So what this one will do is weighted mean. It will give the closest value. Like for example, if you want to plot something here, it will look at the closest value, and it gives a bigger importance than farthest value, for example. So that alpha helps us to weigh the nearest value better. So this is one way of plotting uh, simple smoothing function with alpha a pandas way, or you can use from stats model, use Holtz Winter. um, you can import SES and fit a smoothing function. So you just shift by -1, and then that will generate same thing as this expected weighted mean, exponential weighted mean, right? So that's a simple smoothing method. And then Holtz method. So it what this has in addition to above is sorry, yeah, Holtz method in addition to the above that we saw is it will also look for a trend. So there is a trend component which is missing in the previous one. So you download exponential smoothing and you are fitting in a trend function, and this trend can be additive or multiplicative based on what you have seen. So I'm plotting both of these, and if you use additive, you're getting these values. If you're using multiplicative, you're getting these values. So again, if you plot these, you can see there is our function, and then the smoothing, like it's taking away this zigzagness around it. So it's trying to take the points around it and trying to average it out. So that's essentially what it's doing. But if you include other components, so there are other plots here that are hidden in a way. Our blue plot, which is the number of passengers, the true data, is underneath this green data, and also orange data, which is, so in other words, this double exponential smoothing is fitting really well to the original data. And you can also do triple exponential. You have Holtz Winter. This is called Holtz Winter method, where you have trend and you also have seasonality. You can either fit in an additive model or a multiplicative model. So you can see this is the fit of that, and you can again plot these in this way. If you want to look at at certain interval, in this case I am looking between 1956 and 1959. You can plot it by doing this LOC. You're subsetting the data frame and then plotting the variables that you're interested in. So you can see there is a good overlap with the blue line and this DES additive one, right? So you'll probably fit this one going forward, right? So forecasting, if you want to do forecasting, so far we just try to fit it. We want to forecast now. So I'm fitting training data and saying trend is additive and seasonality is additive, and the period is 12, which is yearly. There are 12 months in a year, so we are looking the season, the peaks are within that 12 months period. So and then to predict, you just call a forecast on this model. So remember, you have to do this fit here as well, and then you can call forecast. And here we are using our function that we created before, which is plot and validate. And you can see this is the test data and this is a predict. They're pretty close, and that of course as you go beyond to the end of this curve, it looks like there's a bigger gap here. So if you want to see what this plot and validate is, again we can look at it here. So plot and validate is here, essentially plotting these three: training, testing, and prediction. And then validate is printing all of these values: MSE, RMSE, MAE, MAPE, right? So this is the mean square error. It actually doing a good job. Mean square error is 0.05, mean absolute percentage error, and mean absolute error is 22.821. This is doing a good job, and you can see based on the fit as well. So now we are going to look into Arima and Sarima. These are in a very regressive way of autocorrelation approach to do forecasting. So there is one concept known as stationary. Stationary data point does not have trend or seasonality. So in order to remove, so if you look at this particular, our original data, this one actually it is has a trend and also seasonality based on what you have seen as decomposition. So if you want to remove stationarity, you can subtract one data point from the other, the lag, and then you will get you can remove stationary. So in this case, I'm removing it once, and here I'm removing it 3 times. So 3 times means, like, for example, you have a time point t1, let's say t1, t2, t3. I'm doing t1 minus t2 comma t2 minus t3 and so on. Or actually, like, maybe this is probably right, t3 minus t2. So now I created, this is diff 1. So if I do it one more time, that becomes diff 2 and so on. So that's what essentially this is doing. So there is a test by you can add you can import this add fuller package and do add fuller test to know whether the particular values are stationary or not. In this case, we know that this is not stationary. So let's say we want to fit directly the data set without actually doing any difference. So we can see, when we print this add fuller, you will get this particular a series of values. So it's not easy to understand, or it's easy to forget. But the second value here is a p value, which for the null hypothesis. So here null hypothesis is the series is non-stationary. So then, because it's 0.99, we are accepting it. So which is true, that there is a trend and stationary. So it's non-stationary. The passenger data is non-stationary, and that is known in this p value. So if I do the difference once, you can see the p value is reducing, but it's still about 0.05, greater than that. If you want to be very strict about it, you can do one more difference, and after doing 2 more differences, this is what you're getting. P value is to the power of minus 16, which means you're rejecting the null hypothesis that it is a non-stationary, which means since you're rejecting, you are accepting that it is in stationary. When you reject it, it's stationary, right? So this is what you want to be looking into, the second value. These gives, so this is the ADF statistic, right? So you can look either this value and compare against what percentage it falls into, or you can look at the directly second value and decide on whether you're accepting or rejecting the null hypothesis. So if you want to understand what these values are, you can essentially look for the help on add fuller, and you can see it's what these values are. So the return size, so the first one is test statistic, the second one is p value, that's what you are looking at, and then it is generating different other values. So if you want to group by a month and look at how many are there, so this is the variation in a way. And then these, you can see there is a trend, and in July and August there are more passengers compared to, let's say, November and February. So these are the other plots people often look at. These are autocorrelation function and partial autocorrelation function plots. Some people can judge autocorrelation. You can say there is something known as P. When you're fitting Arima, you need to understand what is the degree of autocorrelation. So P value that can be estimated from these two plots. So while I'm not going to go into this one, there is an easy way of generating these numbers using auto Arima. So if you have to plot, this is one way to know where the cycles are. You can see every 12, 24 it's peaking again, the correlation is peaking. This one is also correlation, but it's a partial correlation. So for example, if you take this value and this value, the difference is there is a contribution to the value of this one has a contribution to these. There is an association here and also association here. But if you once it has contributed this one, whatever is remaining is plotted here, right? So that is how partial correlation works, and these two are useful in generating what is known as Arima's these P and Q values, moving average, and so essentially you're trying to decide how many lags I need to look into when you're calculating autocorrelations, autoregressions, and moving averages. So for that, these plots can be useful, but AutoArima is clearly easier way to do it. You're estimating through a lot of parameters and trying to come up with the best one. So in this case, when I fit, there is a package known as PMD Arima. You can run it and you can see the best model has autoregressive value of 2 degree difference is 1, and also the moving average of 1. And then for seasonality, there is the number of periods is 2. For seasonality, we have BCD as 1. So if you want to understand what this AutoArima, you can actually maybe we can look at a later time. So here I'm trying to fit Arima model. We are fitting a data and we are specifying the order. The order we calculated from this AutoArima. This is the best fit that it found. Once we have the order, we have the model fit, and then we are doing model that predict, and we are giving the duration it needs to predict. So where does it start and where does it end? And then you have the predictions. I'm converting it to data frame, and then we are using our plot and validate function. You can see that MAPE value is 0.262, which is not great compared to smoothing forecast. So as you can see from the plot itself, this is a flat line. It's not at all fitting very well, which means that the seasonal component is as important or more important than maybe just the trend. So if you want to understand a little bit more about Arima, you can say so you can see here a lot of, so this is autoregressive order, seasonal order, P, D, and Q. D is the differences and Q is the moving, and there is a lot of autoregressive models. A lot of information here. You can see, you can easily read, go through this documentation in stats model, and you will at least get better idea than what is being mentioned here, right? So Sarima is same thing, but here we also fit in seasonal order along with order, and you can give the period as well, and then we more or less do the same thing. We do the predictions and then we are plotting those, and you can see the plot is actually now the plotting looks very well, and also the MAPE value is better than smoothing function as well as the Arima alone, right? So the other one is Sarimax. This X indicates exogenous variable. So one thing that is important about so for example, if you have business data from past 2 years and you're trying to predict next quarter, and you want to predict for every day of the month, then you have to know what those exogenous variables will be. So what could be some exogenous variables? So it could be some holidays, or if you're studying some NFL games, for example, it could be the time of when those games are happening. If there is a cricket match, for example, if you want to know how many people are tuning in, then you want to know whether it falls in a holiday, whether there are other holidays around, or what time the game is being played. If you already have a schedule of when the game is played, then you can actually include them into your future predictions. So this exogenous variable introduction is easy. So here I looked at holidays in a year, and I created this holidays number of holidays per month, per each month. So the first month has 2 holidays, second month has 1 holiday, third month has no holiday, fourth month no holiday, and so on. Because our data set is a monthly level, this is what I did to introduce a exogenous variable. So we have I'm getting train test data, and then I'm adding these num holidays by mapping this dictionary. So I'm taking the month value and then doing this mapping, so that I created this num holidays variable. For the test also I do the same thing. Now I'm fitting Sarimax with train data set, and I'm fitting this exogenous variable, and then with order and seasonal order. And now I'm doing the same predictions as I have done before. So you can see again, it did not actually change a lot, because I think every year has more or less the same number of same holidays, and it did not add any value to number of passengers that we can see. So the trend remains the same, but it's more or less fitting what we expect. So now we'll go to this profit. This is from Facebook, so profit modeling. So here we can import profit function and then do the modeling. So let's look at what are all options available when you are fitting profit. So if you say profit and shift tab, it will show you the definition. So within this profit, you can fit whether the trend is growth is linear or quadratic. This is like a trend. Change points, you can specify at what point it changed. Change point range, yearly seasonality, whether it's auto, or you can specify true or false. Weekly seasonality mode, whether it's additive or multiplicative. Holidays, how many you can include or not include the days prior to holidays, and so on. So there is a description of all of these one, and I would say it's you could look into these in more detail when you're fitting these models. Yeah, so one of the things that a profit requires is to have the data set. So the dates field, in our case a month, year, is actually the day that it has to be named as DS, and the trend value, the number of passengers, for example, has to be Y. So this is hard coded in a way for them. So you're always going to create a data frame in this format, and then try to do prediction. So this is what I did here. I created train, the whole data set I got, and then renamed it to DS and Y, and then I'm splitting the data train DF and test DF. So once I have it, I'm fitting the model, and then here I'm doing the prediction. So one interesting way of doing the predictions is it uses this function called make future data frame. So when you specify the next number of data sets, periods that you need predictions, it will automatically create a data set with those date ranges, and we are specifying the frequency to be monthly, and I'm also specifying don't include history in this data set. So then we are asking it to forecast. The forecast has let me see if it has all of those. Usually it will generate a lot of values like y hat low, y hat upper bound, and so on. So I'm just extracting y hat, and I'm renaming it y, and I'm plotting it here. So we can look at this forecast values here. maybe unless unless I use forecast. So okay, so this is actually coming from neural profit. So let me run this again. So if I do forecast here, see, so the forecast, it will print trend, it can y hat lower, y hat upper. So what I extracted from this is y hat, and there are other components, but we are mostly interested in this y hat, which is the prediction. So that's what we took here, y hat, and then we took the y and then did a created this data frame and then use this function plot and validate. So there are other inbuilt functions like for plotting. This one, if you just say model.plot and you plug in the forecast, it will it will plot the training as these points and then the predictions as this way. And there is another function called plot components. It will do trend, and if you have weekly or daily seasonality, it will also plot them, but it's a yearly, so it is plotting here. And you can also plot change points. So neural profit is more or less a very new package as an extension of Facebook. So it here I won't go through the details, but if you want to fit it, you can just I ran it through this one. So you're saying predict the test data set, and you're in this case the data fields are slightly different. So it is actually you're extracting y hat 1, and then and I'm renaming it to creating a data set, and then I'm saying plot and validate. So if you look at this plot, so it is doing a good job. I think it's a better, even at the end it is doing a better job, but it's not aligning clearly here. So if you can see the map, it's better than some of them, but not as good as let's say either smoothing function or Sarima. So again, you can plot trends and seasonality even from neural profit. So now we are going into this LSTM model. As we know, LSTM is a sequence models from neural networks. So before I fit in the data, I will do a minimax scaler, and I'm doing this time series generator to in a way transform the data. So let me show you one example. So this time series generator, for example, if you have a series 1 to 10 and you want to create a training sample like this 1 2, and then the next sample is 3 2 3, and the next one is 4 3 4, and next one is 5, and so on. So in order to create this kind of a data set, we can use a utility function known as time series generator. So that's what we are making use to fit a LSTM model. Okay, let's go back. So here all this does is it creates a data scaled data, and it's a NumPy array which I'm feeding into this LSTM or neural network model. The number of lags I'm using is 12, and here I created LSTM model, right? So it's a fairly simple model, and you can see the number of parameters here. So this time series, so I'm fitting in the training array, the NumPy array, and I'm specifying how many should be in the input lag. So 12 will be the input data set, and the output will be the next value. So I'm fitting that into saying feed generator, so it will feed in those data, and the number of epochs is 25. So after fitting all of that one, then the prediction is a little bit tricky because you have to feed in the data in the same way. So for the first batch, I'm taking the last values, and I'm I'm trying to predict. And once I get the predictions, for example, here I am predicting for one record, and I'm getting my current prediction, and I'm adding that current prediction to my existing series. I'm skipping the first value and adding from 1 to n. So I'm skipping the 0 value, and then I'm adding this value, right? So the one value will become 0 and this value become the last value. So that's how it is being fit. And then and I'm storing all of those values into preds. And because we have scaled it, so I'm doing the inverse transform and I'm getting inverse scaled. And once I have that, I'm plotting this function in this way. So you can see that the prediction is actually going is actually much bigger than what we were noticing. Maybe it's assuming that the trend is going upwards, but compared to the real data, that the predictions are showing bigger values. So the RMSE or the MAPE is 0.22, which is not at all better when compared to Sarimax. So I did not do any kind of model training or finding efficient parameters. So this is the basic code to run time series data. And this is finally we are doing a XGBoost. So for XGBoost, this is a machine learning model. So we are only given Y. So where do we get rest of the data? So there are many ways of generating new features. So one of them is we can take the date field and we can create whether it's a week or weekday, or now whether it's a quarter, whether it's a holiday. So you can create a lot of these variables, and you can also say how many days from the beginning of the series. Those are all the features that we can create. The other features that you can create are lags. So similar to what I was showing here. So for example, for this Y, these two are the lags, right? So this is first lag and this is second. This is a second lag. And for this data point, this is the first lag and this is the second lag. So these 1, 2, 2, 3, these can be the new features. So exactly like neural network modeling, we can create these. And I did that by using this function shift lag plus 1. So this one will create this one create a data set like this. For example, you see everything is switched around. I'm creating lag 1, lag 2, lag 3, lag 4, lag 5, and so on. So this is these are all 12 lags for each record. So for each Y, we created lags, and those became our X value. So we are trying to fit this X value into our XGB regressor. So we fit X train and Y train, but and then we, very similar to what we have done with neural networks, we try to append the lag and try to predict. Unfortunately, the value you are seeing here, it's not doing a good job. It's more or less like forgetting the seasonality and just maintaining the trend. Maybe I need to do some digging into why this is the case, but it's not doing a good prediction at all. It's finding average. I think for some period it was trying to do something, but after this it became very flat. So that's how we can do XGB. So in real problems, you can pick any of these and try to refine your parameters efficiently, and then you can code it. If you look at Kaggle competitions, a lot of people use XGBoost. And if you want to look at in a different, go to Kaggle and look for some time series notebooks, and you will see a lot of this very much similar structure of all the methodologies. So if you want to learn more, you can get some of those notebooks and different data sets and try to understand what is being done there. So this is simply a toy data set with 140, 150 values, and we didn't even look at how to handle missing data, and what if there is a break, and what if you have to create not monthly but not daily, but what if you have to do every 5 minutes? how do we change parameters. If we want to forecast a really big data set, can these models scale? And we can look into, I think neural profit is just evolving, so we can look into it when it becomes better, because it gives the same structure as the Facebook profit, but it uses a neural network behind the scene. So maybe this has a good prospect of generating good results in the future. So we will look into this. So with that,